the next session. The next speaker is Anosh Joseph from the IJR Moali. He will talk about the complex Langevin simulation of dynamical symmetry breaking in IKKT matrix model. Please start.
Thanks, Junki. I thank the organizers for giving me a chance to speak here. Also APCTP. So yeah, the title of my talk is this: complex Langevin simulations of dynamical symmetry breaking in IKKT matrix model. So these are my collaborators. So here is Arpit. Arpit is my PhD student at IJR Mohali, and Piyush is a master's student at IJR Mohali. Okay, so I need to give a side note. So the side note is a paper appeared in 2020 by these authors. So they also looked at the same model. Okay, so our task is to look at this model using our own in-house developed code, and we also suggest something more. Okay, so which I will talk about later as we move on. Okay. So since this is a focus program on numerical methods, so here I will be talking about complex Langevin method, which is a numerical method. So let's start with the real Langevin method. So what is real Langevin? It was investigated in the context of quantum field theories by Parisi in 1981. So it is a fancy modification of path integral quantization. So the idea is to make use of stochastic evolution of fields in a certain fictitious time, which is known as Langevin time. So let's look at a simple case. Okay, so let's look at an action which consists of only one scalar field, phi. So let's look at this particular action, which contains phi square and phi power 4. So the idea is to study the observables of this model using Langevin method. So we evolved the field phi in the Langevin time tau. So this is the evolution equation, and this is similar to Brownian motion. Okay, equation for Brownian motion. So here we have a drift term, which is this, the gradient of the action. And this is similar to friction in Brownian motion. And we have a Gaussian noise, okay, which is similar to the kick in Brownian motion. So the Gaussian noise eta, it contains quantum fluctuations in the context of quantum field theories. And the gradient term, it is the classical part. So the gradient term is the classical part, and the quantum part is encoded here. And the noise, it obeys certain constraints. So the constraints are this. So the average value of the noise should be 0 when we average over the noise eta, and the correlation should be something like this. Okay. So this is
question. So
yes.
Here, tau is Euclidean time. So you only consider
No. Tau is just a parameter. Okay. We just call it time in quotes. It's just a parameter. Okay.
Then here you have consider time means 0 dimensional.
It's
or
ideally we shouldn't call it time. Okay, this is some continuous parameter. So when we do Langevin evolution, so evolution is happening in this parameter.
Yeah.
Okay, this parameter is increasing as we evolve.
So for example, if you start with like some other quantum field theory in the 1 plus d dimension.
There will be the time of the the time.
Yeah, or Euclidean, then you just omit it. There is some additional like a space time Euclidean.
Right now I am looking at a 0-dimensional theory. Okay. If you look at the action, you don't see any integral here. Okay. Right? So it's a 0-dimensional. It's a toy model. Just
so
to give you an idea. Yeah.
Okay,
so yeah, so we can, in principle, we can study. This can be integral dx dt, d cube x dt. So in any dimension, spatial dimension, we can study in principle. Okay. So now the stochastic evolution, it is making this field to evolve in this stochastic time. So this field is evolved with a probability, which is given by this probability rho phi comma tau. Okay. And the evolution is happening according to this equation. And this equation is known as Fokker-Planck equation. So there is a probability density, and this probability density evolves in this fictitious time, obeying this particular equation. Okay, now, so this is stochastic quantization. It is,
the noise has a delta function, right?
right.
Doesn't that have a normalization?
It's already encoded here, no?
Oh,
No?
it's two.
It's two, yeah.
Okay. Because I was going to wonder where that normalization is in the Fokker-Planck equation, but if you kind of fixed it to a value, then
By looking at this equation, can we fix the normalization? Is that your question?
well, there should be something in that equation that says the noise is normalized to something, and reading it like that, I don't see it. So the question is, I was trying to figure out if it was in which one of the terms it's located.
Yeah, I don't know. I don't know the answer
Okay.
to that. Huh?
Thank you.
Yeah, sure. Okay. So let's move on. So we are looking at quantum field theory with stochastic quantization. So this is a fancy modification of path integral quantization. Okay. So we compute the expectation value of an observable, say O of phi, through this. Okay. So there is a probability weight which is coming like this: rho of phi comma tau, O of phi. And if we assume ergodicity in our system, we can actually analytically show that in the large Langevin time, when this parameter tau goes to infinity, this probability distribution, which is coming through this Fokker-Planck equation, so it should be equal to the Boltzmann weight. Okay, so that we can show formally for real Langevin. So now we are interested in putting this on a computer and simulating and getting some nice physics out of the computer. So in simulations, we discretize this Langevin evolution equation. And this is the Euler first order discretization. That is what we are using. And it takes this particular form. So phi at a given evolution time. So we discretize the Langevin time in this way. So there is a time step and there's a step size. Then the field at say time step n, it is related to the field at time step n plus 1 through this relation. Okay, so where we have the gradient of the action, then we have step size epsilon, then the noise comes in here, okay, with the square root. So this square root of epsilon, that is very interesting. So y square root appears there. Yeah. So this is the evolution in discretized time. Now we need to compute the expectation values on a computer. So we let it evolve in Langevin time. And so the field can start at some point. We can start anywhere, okay? So suppose the field started here at tau equal to 0. Then it evolves. It is gradually finding the region where the action is minimized, okay? So eventually it finds that region and it fluctuates around there. And so in our computation of observables, we need to cut off this part of the evolution. Okay, this is where the field is finding the equilibrium. So this particular time, it is called the thermalization time. Okay, it's the terminology. So remove that part from the evolution and take the average of this, the numerical average, and what we get is the expectation value of the observable. Of course, it comes with an error bar, because we are cutting it off at some t. So it comes with plus or minus something. Okay? There will be an error attached to it, numerical error. Okay, now let's go to complex Langevin. So from real Langevin to complex Langevin. So it is a formal extension of real Langevin. So it was introduced by Parisi in '83 and Clowder in '84. So the idea is very simple. So just extend the field phi, real field, into a complexified field. So it has a real component and imaginary component. So just to double the degrees of freedom. Okay, that is the idea. Then the observable, it goes to this. So this is a holomorphic extension of the observable of the original theory. Then the stochastic equations, the Langevin evolution, it will have two parts. So real part of phi, it evolves in a certain way, and imaginary part of phi, it evolves in this way. And there will be two noises, eta real and eta imaginary. And there are some constraints on this etas. Okay, so it looks like a straightforward extension of the real Langevin. Question? Yeah. So you're saying that something similar to putting the model on a torus, like, yeah. So, right, yeah, of course, we can introduce such boundary conditions. So we need to make the noise, also obey such conditions. So that is straightforward. It can be done. Okay. So now the question is, how do we write the expectation value of an observable in this setup? So we have two types of expressions. Okay. So one is this. So here, this observable, it contains the real and imaginary parts, and it contains it, and it is weighted with a probability distribution containing phi r and phi I. So it is a two-dimensional probability distribution. And here we have the real field with a complex probability distribution. Okay, this is the original theory. Okay, so now these two, if complex Langevin is justified, these two should be the same. Okay. Yeah, so here phi is the original field in the model, then rho phi tau is the complex weight. It's a solution to Fokker-Planck equation such that we get the Boltzmann weight in the large tau limit. Then the second one, which is this. So here, P of phi real, phi imaginary, it's real positive probability of the complex field. So it is happening in the complex plane. Okay, so you have like a two-dimensional distribution. Then this is obtained by analytic continuation of O phi. It's a holomorphic observable. So these two expectation values, they must be equal. Okay, then only we can say that complex Langevin is justified. Okay, so it is not yet proved analytically. Okay? There is no analytical proof so far that you can actually justify complex Langevin. So what we do is we need to check certain correctness criteria when we do numerical simulations. So they have to be satisfied to justify the use. Okay, so it was introduced in this paper recently in 2016. So we follow this correctness criteria in our simulations, and we say, okay, things are matching.
I have a question.
Yes.
Can you go back to the definition of p tau?
Oh, sorry. This one?
So how do you define p phi r phi I tau?
So it is a two-dimensional probability distribution in the complexified field configuration space. Okay, so there will. So your question is, how do we find this probability distribution?
What is the definition of p tau?
What is the definition of this? So the idea is, yeah. So we have a probability distribution rho, okay, for the original field. Okay, and we are going to replace this with a real probability distribution. So this one is complex, okay, and we are asking, can we replace this with a real probability distribution, which contains two variables instead of one variable? Okay, so that probability distribution is this. Okay, now how to define this? So it should come out as a solution of the Fokker-Planck equation. So you need to solve that somehow numerically or somehow. Okay. Okay,
Can I
now
just make a comment? In the
yes.
previous page at the bottom, there are two more authors.
Yes, there are several authors. I just took the first author.
Yeah, the first author is Nagata. Yeah, okay, good.
So I instead of writing all the authors, I just picked the first author. Sorry.
Yeah. Okay.
Sorry about that. Yeah, yeah. Okay. Right. Now let's go to IKKT matrix model.
Before
yeah,
going,
Yes.
so when you
Oops.
say complex Langevin, and do you here then when you calculate the complex Langevin simulation, do you calculate on the right hand side or left hand side?
So let's look at
Here, yeah. So here you define in this way, and when people say complex Langevin, does
Ah,
it mean this
so
is
we so basically we assume that this is justified.
Yeah.
Okay. So we are assuming that this is justified, and we are computing this.
I see.
Okay.
Thank you.
Okay, so let's go to IKKT matrix model, the main theme of this. So we are applying complex Langevin method to IKKT matrix model. Let me give you a brief introduction of this model. So this model was proposed as a non-perturbative formulation of superstring theory in this paper. Okay, Ishibashi. There are IKKT 4 authors in this paper. I just took the first name, the first person in the paper. So this is also known as type 2B matrix model. So in this model, space-time, so in this paper, it was shown that space-time emerges dynamically from eigenvalues of bosonic matrices in large n limit. Okay, so this model contains n by n bosonic matrices, and there are 10 such matrices, Hermitian matrices. And in the large n limit, when n goes to infinity, the size of the matrices, they become infinite. And space-time should emerge dynamically, okay, from the eigenvalues. So that is the idea. Space-time has certain number of large dimensions and certain number of small dimensions, compactified dimensions. So we can study the scenario of dynamical compactification. Okay, so certain directions are compactified dynamically, and we can treat that as a purely non-perturbative effect. Okay, and we can put our model on a computer. So like similar to what Raghav mentioned in his previous talk, we can study this on a computer. Okay, non-diagrammatic approach. Okay, so we can probe the non-perturbative regime of the theory. So this model contains a description of an arbitrary number of D objects. So these are D0 branes, D1 branes, etc. So in a matrix of this model, these block diagonals are the D objects, and the off-diagonal elements are the interactions. They encode the interactions between these D objects. So just a review of IKKT model. So where is this model coming from? So this model is coming as a dimensional reduction of 10-dimensional super-Yang-Mills theory. Okay, so you start with a 10-dimensional theory. It contains a fermion and a gluon and a gluino. Then you dimensionally reduce this to a point. Okay, space-time is just a point, and you get the aggregate model. So this is the action of the model. So there is no space-time integral because it's a 0-dimensional model. Okay, yeah, there is no space-time. Space-time is just a point. So this is the bosonic part of the action. So it contains the matrices, 10 by 10 matrices, n by n matrices, and there are 10 of them. So x mu whole square, gauge group is SUN. So this is a fermionic part of the action, psi bar, gamma mu. These are 10-dimensional gamma matrices. Psi bar psi, and psi bar and psi, they are related through some constraints. These are Maillard-Weil fermions. So this is the action. So let's look at the symmetries. So this action contains SUN gauge symmetry. So the scalars, the matrices, they transform in this way, and the fermions, they transform in this way. So here mu is running from 1 through 10 and alpha from 1 through 16. Okay, there are 16 fermions. It has SO10 Lorentz symmetry because it's coming from a 10-dimensional theory, but the Lorentz symmetry becomes an internal symmetry once you reduce it to just to a point. Then it also has supersymmetry. Model is supersymmetric. It's maximally supersymmetric. There are 16 supercharges. So these are the symmetries of the model. Question?
Maybe it's a very basic question.
Okay.
So because I'm not familiar with IKKT, this PFSS model, I can understand, but here, when you say gauge symmetry, you say just zero.
It's at a point. Everything is at a point.
So it is still, maybe it's a communal, but might be communal, but the chemical is gauge.
Not really, but it's a remnant of gauge symmetry.
So
Okay.
in the end, you are just
There is no
consider
gauge field in this.
Yeah. So just
So it has an SUN symmetry. We can say that.
symmetry and consider the singlet vector of them, or I mean singlet part of the this.
It has to be gauge
SUN.
invariant. Everything has, because there's a trace, right? So things are gauge invariant there. Okay, there's a trace. By the way, BFSS is coming from if you dimensionally reduce BFSS to a point, you get this. Okay, so BFSS is a quantum mechanics model, and you reduce it to one point, and you get this. Okay. Yeah. So this model has 10 bosonic matrices X mu. The question is, it has SO10 Lorentz symmetry, and certain directions are compactified and certain directions are large. So how can we realize this in this model? So it can be realized dynamically, okay, or non-perturbatively as the breaking of this SO10 Lorentz symmetry. So the breaking could be SO10 breaks into SOD cross SO10 minus D, and D could be, it could be anything less than 10. Okay, so there is a breaking pattern, and the breaking is happening dynamically. Okay, and can we see this pattern, this breaking pattern, this spontaneous symmetry breaking pattern through complex Langevin simulations? Okay, that is the idea. Okay, now let's look at the partition function. Partition function is given by this. Integrate over the bosonic degrees of freedom, fermionic degrees of freedom, and we get a number. Okay, there is a partition function. Now let's first integrate over fermions. So there is no psi bar psi, there is only psi, because psi bar and psi, they are related. Okay. Now integrate over fermions, and what we get for this particular model is a Pfaffian. Okay, not a determinant. We get a Pfaffian, which is square root of the determinant. Okay. So this is a matrix. It is an antisymmetric matrix of this much size. Okay, we have 16. It's 16 times n square minus 1. This is the matrix size. And this matrix can be complex in general. Okay, it is not real. So now if you want to simulate this using Monte Carlo, since this matrix is complex, we have a sign problem, okay, or complex action problem. So we cannot do naive Monte Carlo simulations for this model. And this is the same with the BFSS matrix model. Okay, we can, it has a sign problem, mild sign problem. Okay, when we do Monte Carlo. So again, how do we represent M? So it is represented through this linear transformation. Okay, M acting on psi, it has to act in this way. Now let's bring this Pfaffian to the exponential. So exponentiate and take the log. Okay, so we can express the action as an effective action, and this effective action is given by this log of the Pfaffian of M, and Pfaffian of M is complex in general. Okay, so basically we need to sample field configurations with this weight, this complex probability weight. Okay. Now the bosonic action, it is trace of x comma x commutator square. Okay, so there are configurations where this x's commute, and these are known as flat directions. So the bosonic action has flat directions, but the partition function is still finite, even with flat directions. So this was shown in these papers. Okay, in the IKKT model, we can have finite partition function. Now let's write the Pfaffian in this way: the polar decomposition, the absolute value of the Pfaffian, and times a phase. Okay. Now, if you want to do Monte Carlo, what we can do is we just remove the phase, just ignore the phase, okay, and sample using this. So then the effective action is real. We can do Monte Carlo, and also if theta is close to 0, we just ignoring the phase is okay. Okay, it will produce results that are close to what we want. Okay, but if theta is large, if the phase fluctuates strongly, then there is a problem. We will not get correct results. Okay. So in our model, the theta fluctuates strongly for SOD with large D. Okay. So this D, maximum value of D is 10. Okay, SO10, and it can break into some smaller SOD and SO10 minus D. So when D is large, the phase fluctuates wildly. Okay, so then there is a problem. So people have studied this model, IKKT, in the past, especially Jun Nishimura and the collaborators. So they have looked at it. They have written many papers on this. So they, in 2015, they studied this using Monte Carlo after removing the phase. Okay, and there they found that there is no spontaneous symmetry breaking in IKKT model when you remove the phase. Okay, so this is telling us that the phase plays a role. Okay, if there is a spontaneous symmetry breaking, the phase is responsible for that. Okay, phase of the function. Then bosonic part of IKKT, it was studied in this paper. So they looked at it using Monte Carlo and Langevin. Okay, just remove the fermions, you get bosonic IKKT, and there also they found no spontaneous symmetry breaking. Okay, so again telling us that the phase of the Pfaffian plays a role.
You mean when you say bosonic IKKT, you just
remove the fermionic
remove
part of
from
the
by hand and just
by hand. Yes, where is the action? Yeah, just remove this part. Okay, set this to 0, then it's bosonic IKKT. Okay, so then the full IKKT with the phase included, it was studied recently in this paper. Okay, a recent paper. So there they found that this model has SO3 symmetric vacuum. Okay, so this SO10 breaks into SO3 cross SO7. Okay, so this is what they found in their simulations. Okay, so 3 directions are becoming larger. Okay, so there in their study they introduced mass terms to the action to control certain technicalities in simulations, and they took the 0 mass limit to get the results. Okay, so now we also study the model using complex Langevin method. So it serves as an independent check. Okay, so far nobody has checked this. They produce this result, and it is good to have a cross check. Okay, so that is one idea. So it serves as an independent check. So our code is written in C++. So we started with a small code that can run on a laptop, a serial code. Then we expanded that to a parallel code. Okay, now this code can run on a cluster or a supercomputer. Okay. So that is the idea. So try to cross-check the result, and also we suggest supersymmetry preserving mass terms. Okay, so in their work, their mass terms were not SUSY preserving. Okay, so it is good to have SUSY preserved when you do numerical simulations. Okay.
I mean, you preserve the supersim lattice or the field theory.
Here, the lattice is just a point. It's a 0-dimensional model.
Yes, so I just say because you will discretize your model. Yes.
But here there is no space-time. So then I don't know what you mean by this. Okay. Yeah. Everything is happening at a point. Okay. But if you're looking at BFS's model, then yeah, there are problems. Yeah. Because you have a time direction. Yeah. Okay. Now, what is the Langevin evolution? So we need to evolve this bosonic matrices in Langevin time. So Langevin evolution is given by this. And here the effective action is complex. So once we evolve this thing becomes complex. Okay, X mu becomes complex. So here eta is a Gaussian noise. It's drawn from this ensemble with this joint probability distribution. Okay, so now let it evolve, and we need X mu of tau for large tau.
Is there
Yes.
a reason why you're using the orthogonal GOE? Is it because the X is here real? Or?
This is simplest we can have, because we are our noise should be Gaussian. Okay.
Yeah, actually, yeah, my question is previously you mentioned that it's complex Langevin, and I imagine some fields might
Yeah.
need a complex for here you are still consider real field.
In our simulations, we take the noise to be real. We just set the complex noise to 0. It
Because
doesn't make any difference.
X is also because X is still real.
X is complex. It evolves into complex. Yeah, because the action. Sorry,
Permission.
this is complex. So this entire
Okay.
term is complex.
Okay.
So then this is complex.
Then why you choosing the GOE like a GOE or other?
This is the simplest we can have.
Okay.
If we use GUE and things like that, I don't know. There may be problems associated with that. So one has to study carefully. So we picked the simplest one, simplest noise. Okay. So now the discretized version of the evolution is this. So we have Langevin time step delta tau, evolve. Then we choose this delta tau to be adaptive, in the sense it's not fixed. Okay. So sometimes it can be large, sometimes it can be small, depending on where you are in the field configuration space. Okay. And the size is determined through the size of the drift. If the drift is too large, we take the step to be too small. Okay. So it is to avoid some subtleties in the evolution. Okay. This was introduced by Arts and others in this paper. So we make use of that. So now we don't know whether we can trust our results or not. Okay, so because there is no analytical proof for this complex Langevin, so we cannot know a priori whether the results are reliable or not. So this X mu, the Hermitian field, it can develop large anti-Hermitian path during Langevin evolution. So that means it can wander off to SLNC from SUN. Okay, so it can wander off to imaginary directions. So we need to introduce some correctness criteria to check this. So what we do is, so this was introduced in this work, Nagata and others in 2016. So introduce a magnitude of drift, which is given by this. So this is a drift, take the absolute value and normalize. In this way, we have 10 matrices. That is why 10 is coming here. Then the magnitude of the drift, it should fall off faster, exponential or faster. Okay. So look at the probability distribution P of U, which is coming from this, and this probability distribution should fall off exponentially or faster. Okay. So that is one correctness criteria. So we always monitor in our evolution whether it's falling off that fast or not. So this is a sufficient condition for correct convergence of complex Langevin. So it was shown by Nagata and others in this reference. Then, so there are certain problems when we put this on a computer and try to simulate. One is the excursion problem, which I already mentioned, that things can go off into imaginary directions. So it must be controlled. Now, how can we control this? So it was introduced through gauge cooling. Okay, so the process of gauge cooling, it was introduced here. Again, complex Langevin started taking off from, I think, 2007 onwards. Okay, there was an explosion of lots of papers. People were working on various aspects, how to control this, all those things. So gauge cooling was introduced in this work. So what we do is we track the deviation of the matrix X mu from Hermiticity So it is going to SLNC from SUN. So there is a deviation from hermiticity, and this number, it captures the deviation. Okay, so we track this norm, the hermiticity norm. So we see that observables and the drift, they are invariant under this transformation. Okay, so G is an element of SLNC, but the norm is not invariant under this. Okay, now we can exploit this property to minimize the deviation from hermiticity. So what we do is apply gauge cooling process. So this amounts to apply finding a new field x mu tilde through this process. Okay, so here G is taken as this. These are the generators of the group. Then FA is given by this. Okay, and alpha is a number. This number could be constant or adaptive depending on the simulation. So we apply the gauge cooling again and again, and we bring this closer to SUN. Okay, from SLNC to SUN. Now the evolution is gauge cooled. So the gauge cooled evolution is given by this. Okay. Now if you make alpha adaptive, it leads to a faster evolution towards hermiticity. It was shown in this work. So we use adaptive gauge cooling. Okay? These are all part of the numerical technicalities. So in our simulations, hermiticity norm is under control. Okay, it's not blowing up. So we simulated this for number of colors or the size of the matrix, 2, 3, and 4. So we did not have a big computing power at that time. So we started with small number of colors. Okay. So x-axis is Langevin step size, Langevin steps in units of times 10 power 5, and this is the hermiticity node. So the things are under control. Okay, they are not blowing up or anything. Then the next problem is singular drift problem. So this problem happens when eigenvalues of the fermion operator, they accumulate too close to 0. Okay, so if you look at the evolution of the effective action, it has a fermionic part and the bosonic part. Okay, the fermionic part of the evolution, it has this form, and here the matrix M inverse appears. Okay, so in our numerical computation, this is the costliest part. Okay, finding M inverse. So it takes a lot of computational time. So in the simulation, most of the time is spent here, okay, finding inverse. So we use conjugate gradient algorithm to find the inverse of the matrix. Okay, we don't directly compute the inverse, we compute it iteratively. So singular drift problem, we can avoid this problem, accumulation of accumulating the eigenvalues close to 0. We can avoid this by adding small mass terms to fermions. Okay, so add some mass terms so that it is shifted away from 0. Okay, yeah.
You use conjugate gradient to solve the inverse matrix in your program.
Yes.
And you do not do any truncation.
There is a tolerance. You introduce a tolerance. Yeah.
Okay.
Up to a certain tolerance. Okay. If it falls below that, we accept this as the inverse.
Okay.
Here
Yeah.
you adding small mass and numerically you decrease mass to 0 or.
Yes. Yeah. Eventually, you need to take mass point to 0. We will come to that.
I see. So here you mentioned that it's a supersymmetry, proper target supersymmetry. Right?
Yeah, it will break supersymmetry depending on what type of, in which way you are adding the mass. Right? So we will come to that soon, how we can preserve supersymmetry. Yeah, so now coming to mass terms. Okay, so deformation terms. So we need to use mass deformations to simulate the model reliably. So now we look for the simplest type of deformation. So the simplest deformation would be Gaussian type deformation. Okay, there'll be x square with some mass matrix and the psi bar m psi. Okay, with some 3 comes because of there is some structure there. So this is the simplest deformation. Then add this to the action delta s, but adding delta s this Gaussian type, it breaks, it breaks supersymmetry, okay, that particular Gaussian delta S. So our suggestion is use supersymmetry preserving deformation. Okay, this is similar to the BMN deformation, what David and others did back in the days. So introduce supersymmetry preserving deformation, and it was mentioned in this work, okay, for this particular IKKD type models. So that type of deformation, it will have three terms. So there will be Gaussian terms. The first two are the Gaussian type deformations, and the third is like a Myers type deformation. Okay, so these are the structures, how they should look like, so that supersymmetry is preserved in this. Okay, so there is a deformation parameter which is mu. Okay, so there is only one deformation parameter in this particular deformation. Okay, so we can add that to the action. Now, when mu, the deformation not equal to 0, we have a manifestly SO7 cross SO3 symmetry, okay, instead of SO10. But we can take mu going to 0 limit. Then we recover SO10. Okay. So now we can probe spontaneous symmetry breaking in this IKKD model. First taking n going to infinity, large n. Then after that, we take the deformation going to 0 limit. Okay. So this is still work in progress. Okay, so we are still looking at the code is there and simulations are ongoing. Question? Yeah.
Here you start with the non-zero mu, and the SO10 is broken explicitly
In this way because of the mass terms, yeah, the deformation terms.
And then later
You bring the deformation to 0. Then you recover the original IKKD.
And then you expect some spontaneous symmetry.
Exactly, in IKKD. Yeah. That is the idea.
I just wonder, like here you start from the explicit broken,
yeah.
And then you expect some other spontaneous symmetry breaking, and you proceed, right?
Yes, when mu equals 0, it becomes IKKD, and then you ask, when it becomes IKKD, if symmetry is not broken, they all should converge to the same value. Okay. And if they don't, then there is a spontaneously broken symmetry. Okay, and the reason for adding this is we need this in order for our simulations to work. Okay, that is the reason for adding this. Okay, to simulate it reliably. Okay. Now, in our simulations, similar to what these authors did in their 2020 paper, and also inspired by this work, we use Gaussian type deformations. Okay, we just remove the Myers term. So this is not supersymmetric. Okay, if you remove the Myers term, it is not supersymmetric. So these are the structures. Yeah. Now, what is the form of this matrix A? The form is constrained. So it is coming again from because of Majorana-Weil fermions. It was shown back in the days in this paper. So the form of A has to be constrained in this way. Okay. So now again, for the bosonic case, we introduce mass terms in a particular way. Okay. Again, to keep track of, if we can put random numbers here, randomly chosen mass values, but then things will be spread out everywhere. Okay. Then it's not easy to track. So then, so we picked something that has this SO7 cross SO3 already encoded in it. Okay? And eventually we'll take mass going to 0 limit. Okay, so we select this M unit row, the 3 form in this way. Then we have delta S. It has 2 deformation parameter, epsilon and MF. David, do you have a
Could you go back a second? You have the bosonic mass terms. Yeah, I see an SO3 symmetry and an SO4 symmetry.
Yeah,
but the one
they are
4 also kind of breaks
right.
the
Yeah.
symmetry
So
further.
yeah. So yes, so it already has an SO3 in it and SO4 in it. Okay, so this is again the fermionic deformation already has a broken SO7 and SO3. Okay,
right, but this is further breaking in the bosons.
it already contains SO3 and SO4, this one.
Yes,
Huh?
but that's extra breaking from SO3 because
Yes, in the scalar sector, yes,
Yes.
coming through, yes. So what I'm saying is we have several options. Okay, one option is making everything different. Okay, if you make everything different, later on I will show one plot where things are kind of spread out. Okay, and it's not easy to track the convergence. Okay, so then we introduce something that is already there, already, you know, that is broken there. So that is one motivation for picking this particular set. Yeah. So yes, we can. This is under our control. We can pick whatever we want. And in our, you know, when you write a paper, you should look at various possibilities, and you should show that they all converge to the same result. Yeah. Okay. Yeah. So this deformation breaks explicitly SO10 to SO3, SO7. Yeah. So now simulations, we are looking at how the drift, the probability distribution of the drift, how they are falling off. And here we can immediately see if we set the deformations to 0, the drift is going like this. It's not exponential. Okay, it's not falling off exponentially. Now, so these are various values of MF and epsilon, again, MF epsilon. So here, in this case, required fall off is not %. So that means we need to introduce an MF. Okay. Then here, the required fall off is % in this region here. Okay. So these are MF equal to 2 and epsilon greater than something. Green is 0.2. And again, epsilon equal to 0, MF equal to 2, fall off is not %, fall off is not %. So we cannot trust this the data. So we just throw away this data. We cannot trust. Okay, and we take only this, the data corresponding to this. Okay. So we did the simulations for n equal to 2, 3, 4. Again, we wrote the code from scratch, and we want to check our code, make sure that everything is working. So required fall off is % for MF equal to 2 and epsilon 0.4. Now, what are the observables to track this spontaneous symmetry breaking? So the observables are this. Okay, there are 10 such lambdas. Mu is 1 to 10, and these are called radial extent of eigenvalues. Okay, it has some meaning why it is called radial extent. Okay, from string theory side, it has meaning. So we use this as our observables, and we measure this in our simulations. Now, what is the plan of action? So first, MF equal to 0, then take large and limit. Then from there, take epsilon to 0. Okay, so this should restore the symmetry up to SO7 cross SO3. Okay, then take MF going to 0. So then it should restore the symmetry SO10. Okay, so that means because the theory corresponds to the undeformed Ikkt, the original Ikkt. So then, so we are monitoring lambda mu. So make all these extrapolations. Then from this lambda mu, see if SO10 is broken or not. Okay, so that is a plan of action. So consistently, one by one, okay, we need to check this. Now, coming back to simulations. So first we tried the Bosonic Aggregate model. Okay, so decouple fermions from Ikkt, what we get is Bosonic Aggregate, which has this action, and there is no SSB in this model. Okay, so it was shown in this reference using Monte Carlo and 1/d expansion. Okay, so 1/d is you take the number of the matrices as d, and d as a parameter, and do 1/d expansion. Okay, so analytically, one can show using 1/d expansion and using Monte Carlo that there is no SSB. So we asked, can we reproduce this, okay, in our simulations? So this is our simulation results. So we see that spontaneous symmetry breaking is absent. So these are the 10 lambdas, okay? And this is the analytical result coming from the 1/d computation. It is close to 0.25. So there is no SSB, okay, in Ikkt, because they are all clustered together and they are approaching the analytical value. So this is 1/n, and these are the n values we used. we used up to 64, n equal to 64. So next, another thing to observe is the bosonic action. So from 1/d expansion, the analytical value is this 2.5. And in our complex Langevin simulations, we can see that the real part is fluctuating around 2.5. Okay, this is n equal to 64, and the imaginary part is 0 because it is real, action is real. So we looked at the fall off of the drift. So they are all falling off faster than exponential, which is a good sign. So simulations are reliable. Now let's go to APCTP model simulation results. So this, so in 2015, these authors of this paper, they looked at the phase quench model. They just removed the phase and they studied using Monte Carlo, and they found no SSB. Okay, in phase quench model. So again, yeah, symmetries of the model for various parameters. So when epsilon equal to 0, mf equal to 0, we have this symmetry SO10. So in our simulations, we can define an observable. Okay, there's some kind of normalization. So take the lambda mu, these are the observables we want. So we want to reduce the epsilon dependence as much as possible. Okay, so for that, we take this ratio and define as rho mu. Okay. And this ratio removes the epsilon dependence to a certain extent because we are taking epsilon going to 0 limit. Then we monitored the Langevin history. So this for n equal to 4, mf equal to 2, epsilon equal to 6. So they all look fine. Okay, they are fluctuating around something. We removed the thermalization part. This is after the thermalization cut. So here, I would say some autocorrelation is there, present here, here also, but these two, they look perfect. Okay, in simulations. So the way we compute data is you have to find the autocorrelation time, then you take the gap, that as the gap for your measurements, okay, so that the memory effects are not there. Okay, now the idea is to take the Largen limit, n goes to infinity, epsilon goes to 0, mf goes to 0. If no spontaneous symmetry breaking in the system, then all rho mu's should be the same. So we did the simulations for n equal to 4. So from the structure of our mass terms, so what we are seeing is this. So we can take the average of the first three because of that 0.5, 0.5, 0.5. They fluctuate around the same value. Then we have rho 4, 5, 6, 7, then 8, 9, 10. Again, there's a symmetry we can average. So what we see is certain directions are expanding and certain directions are shrinking. Okay, so something is happening. So now, since we did this for one fixed n equal to 4, ideally we should go to large n. Okay, so we are not doing the large n extrapolation, but we can do epsilon going to 0 and m of going to 0 limit for a given n. So when epsilon going to 0, if there is no SSB, we should get this SO7 cross SO3. Okay, so that means the first 7, they are the same, and the next 3, they are the same. Okay, but we see that for n equal to 4, that is not the case. This equality is not there. Okay, so something is happening. So growth and shrinkage of extents along some directions. So they are telling us that some kind of SSB is there. Okay? So we need to confirm this. Again, this is a preliminary study. So we need to do large n simulations. So that is ongoing. So we recently got access to a supercomputer. So we are, the code is they are running. Okay? It can be, we can run that in parallel mode. So simulations are ongoing. So we hope to report the results. So again, these are some drift plots, whether we can trust the data. So we see that the singular drift problem is there. If you reduce m of less than 1, and if you reduce epsilon less than 0.2, then it's problematic. Okay? Complex Langevin is not reliable. So one has to be careful there. So this is our the data so far tabulated. Okay. So if we extrapolate to epsilon going to 0 and m of going to 0, what we get is this. So we see a grouping there. This is slightly shifted. This thing should be the first 2, and this should be the last 4. Okay. So we see some kind of grouping. Okay. So this is telling us that SSB is present. Okay. Also, the recent results from this paper, it suggests that it is broken down to SO3. Okay, but what we are seeing is slightly different. But again, it's a preliminary study. Okay, so this is the reason why we need an independent check. Okay, so it's a preliminary study. I'm not saying anything conclusive. The simulations are still ongoing. I'm sorry. Sorry, I'm not following your question.
The recent result is also for a lattice.
Yeah, yeah,
Okay.
exactly. Yes, yes. When I say lattice means a point, okay, space-time point. Okay. Yeah, so we need to do simulations with SUSY preserving deformation, BMN type. Okay, that is another thing we need to do. So the advantage is there is only one deformation parameter instead of two, epsilon and m. Okay, and the extrapolation to large N and 0 mu will be 2 parameter instead of 3 parameters. Okay, which is again a good thing. Okay, less number of parameters always good. So let me conclude with final comments. So complex Langevin is a useful tool to study models with complex actions. And we found that Bosonic Aggregate model, it has no SSB in large N limit. And it supports the claim that the Pfaffian, the phase of Pfaffian plays a crucial role in SSB. So we found some presence of SSB in full aggregated model. It's a preliminary result. It still has to be, fine-tuned and clarified. Large N simulations, they are needed. And we can also refine the results by introducing SUSY preserving deformations. Okay, this is what we are suggesting. We should introduce deformation terms so that SUSY is not broken. So that is all. Thank you.
Excuse me, can I ask a question?
Yes.
Yeah. So what is the signature of the metric signature?
So here it is Euclidean aggregating. So the contraction is done through delta mu nu. It is not Lorentzian aggregating. So one can study Lorentzian aggregating as well, where the contraction is done through eta mu nu, minus plus plus plus. Yeah.
Okay. Yeah. Then so do you have something like a time component matrix, something related to that?
You mean Lorentzian aggregating?
I mean the Euclidean. I mean, how? Or do you just ignore the time direction completely? Just.
I don't understand your question. Everything is
I mean,
happening
the imaginary time direction.
there is no time direction in this model.
Oh,
Everything
okay.
is happening at a point. Space-time is a point.
Oh, okay. Yeah, yeah. Thank you.
Yeah, yeah. Okay.
So, is there a question? So I have a question.
Yeah, yes.
Can you using this complex Langevin to DFS estimation?
Of course, that is our next goal. Yeah.
Oh,
So our next goal is to increase the difficulty slightly and look at the BFSS model without removing any phase from the fermion operator. And we can check how severe the sign problem is. And yeah, so I don't think anybody has studied this. So Jun is, I see Jun Nishimura here. So maybe Jun is also focusing on this, maybe, I don't know. So that is something interesting to look for, yeah, BFSS. Also BMN, I would say, BMN model, full BMN model. Yeah. So now we have this tool, complex Langevin method, fairly new, and we can apply this method to these models. Yeah.
Excuse me, this is June.
Hi, Jun.
Hi, can I make a small comment about our work that you
Oh, sure, Jun.
do in your talk? So in our paper, JHEP paper in 2020, we went up to n equals 128 and made a Largian extrapolation first. And then we tried to see the SSP. And then our conclusion was that SO10 is broken down to SO3. And well, of course, it would be nice to cross-check this result, but so far what you have seen is, I think, just finite n effects. So
Right. Could be. Yeah.
yeah, so I think you should carefully look at large n. And
Definitely. So we are, so simulations are ongoing for large n. So at some point we had problem finding, a computer cluster to simulate. So now that problem is solved. We have access to a supercomputer. So yeah, certainly we are looking at large n.
Yeah, that would be very nice. And another thing I would like to ask is, have you already simulated the SUSY preserving deformation?
No, it is still ongoing. Still ongoing. Yes. Yet to report on that. Yeah.
I see. So it would be nice if you can make the complex Langevin method work for larger parameter region if you use this deformation. So I'm looking forward to that.
Yeah. Okay.
Yeah, thank you.
Sure.
Is there any other question or comments? If not, let's thank speaker.